A very good evening to all the respected speakers, faculty members, researchers, and participants joining us today. On behalf of the North Cap University and the organizing committee, we warmly welcome you to day 4 of the ATAL Online Faculty Development Program.
We sincerely thank you for your continued dedication. Today's sessions mark a transition from system design to material science, covering the critical journey of VLSI design flow and the pivotal role of nanomaterials in the next generation devices. My name is Krishika.
And my name is Shivam, and we are delighted to invite you to be part of the fourth day of the ATAL Faculty Development Program, which brings together academia and industry experts to share knowledge, insights, and emerging perspectives in the field of semiconductor technologies. This faculty development program is a pivotal initiative in the context of India's rapidly evolving semiconductor landscape, which is poised to emerge as a global leader in chip design, manufacturing, and innovation. As India strengthens its semiconductor mission, developing a strong understanding of technologies spanning design to packaging has become essential.
The FDP offers comprehensive exposure to critical areas such as clean room technologies, vacuum systems, and semiconductor fabrication processes, including lithography and etching, along with advanced topics like EDA tools, AI and machine learning applications in VLSI, and the complete design flow from RTL to GDS2.
Participants will also explore semiconductor packaging, nanomaterials, and analog and mixed signal VLSI design, gaining insights into both foundational and advanced aspects of semiconductor engineering.
Through expert-led sessions on global market trends, India's semiconductor assembly and testing ecosystem, emerging industry developments combined with interactive discussions and practical insights. This FTP aims to strengthen research capabilities, teaching excellence, and industry collaboration, contributing meaningfully to India's vision of self-reliance in semiconductors. It is now our proud privilege to welcome our first speaker for the day, Ms. Nikita Gulia, joining us from the industry sector.
Ms. Gulia is a senior RTL design and verification engineer at Agnesys Technologies with over 9 years of industry experience. She holds an MTech in VLSI from CDAC Noida and is a recognized expert in system RDL, RTL design, and UVM based verification.
Beyond her core engineering role, she has extensive experience in delivering technical trainings to customers and companies across the globe. Her research contributions also include multiple published papers on register design automation techniques.
With her deep hands on experience in the industry, she brings practical insights into the complex workflows that power modern chip design.
Today, she will be delivering Technical Session 7 on the topic VLSI Design Flow from RTL to GDS2. This session promises to unravel the journey of a chip from its register transfer level description to the final GDS2 output ready for fabrication. The chat box will remain open and the Q&A session will be taken at the end. We invite Ms. Nikita Gulia to kindly begin the session.
Thank you for the introduction. Can you see my screen and hear me?
Yes, ma'am.
Welcome to the session on VLSI design flow from RTL to GDS2. Let me start with the basic idea of what VLSI means. VLSI chip design is about arranging millions or billions of tiny transistors on a small piece of silicon. Even though a chip looks small, internally it is extremely complex. Broadly, there are two main types of digital chips. The first one is ASIC or application specific integrated circuit. These chips are designed for a specific function or cannot be changed after manufacturing, like the mobile phone you must be carrying in your hand or the laptop in front of you. The second type is FPGA, which stands for Field Programmable Gate Array. These chips are reprogrammable and are often used for prototyping or flexible applications, also used for testing. Designing a chip is not just about writing code, it is a complete structured process. From defining requirements to designing and verifying the logic to finally creating the physical chip. This process is called the VLSI design flow. In this presentation today, I'll explain what the VLSI design flow is, how it works, and some common terminologies, keeping everything at high level. Now that we know what a VLSI chip is, let's understand what we mean by the VLSI design flow. The VLSI design flow is a structured, step-by-step process used to design and manufacture integrated circuits with millions of transistors. Because these chips are very complex, they must follow well-defined methodology. The flow is divided into multiple stages. It starts with the specification, where we define what the chip should do. Then comes the design, where the behavior is described using hardware description languages. This is followed by verification, where we check the design works as intended. Verification plays a key role throughout the flow. At high level, it ensures the design meets specification and can later be converted into a gate level form called a netlist, which tool used for implementation. As the design progresses, the flow branches into different areas. Fabrication and testing are part of production, while placement and routing belong to physical design. Finally, it's important to remember that the design flow is iterative. If issues are found, the design is corrected and redefined until it is ready for manufacturing. Working of VLSI design cycle, starting from the chip design specification to logical implementation synthesis to placement and route to design layout. Uh, so now let's look at how the VLSI design cycle works, focusing mainly on ASIC design flow. The main goal of this process is to convert specification into real silicon. It begins with requirements collection, where we define the chip, what chip should do, along with PPA, the performance, power, and sometimes cost targets. Clear requirements are critical for successful design. Next comes high-level architectural design. Here, the chip is divided into major blocks, and decisions are made about data flows and interfaces without going into detailed coding. After that, the designers write RTL code using languages such as Verilog or VHDL. RTL describes how the system behaves on each clock cycle. Once the RTL is stable, synthesis converts it into a gate level netlist from registers to gate using the target technology. The design then moved to physical design, where placement and routing decides the actual layout of gates and wires on silicon. Throughout the flow, verification ensures the design works correctly. And finally, after all checks pass, the design is sent to the foundry to be manufactured as an ASIC chip. So overall, this is structured step-by-step process where verification at every stage is crucial. Uh, and this is the complete steps of chip design flow, starting from chip specification, design entry, RTL partitioning, to clock tree synthesis, placement stage, floor planning, DFT insertion, routing stage, final verification to GDS2. Now let's look at the complete chip design flow step by step. And this slide gives a bird's eye view of the entire journey from idea to silicon. I'll briefly explain each step and we'll go into more details later. We start with the chip specification, where we can define functionality, clock frequency, power, area, and any other special requirements. Next is the design entry and functional verification. Here, designers write the HDL code using RTL languages, Verilog, VHDL, and verification engineers verify the design to ensure that it is behaving correctly. RTL design describes how data moves between registers on each clock cycle. This is main working level for digital designers. After that, the design is partitioned into smaller blocks to make it easier to manage and optimize. Next is design for test or DFT, where additional logic is added to make the chip testable after fabrication. Once the logical designing is complete, we move to physical design. This starts with floor planning, followed by placement, clock tree synthesis, and routing. After routing, final verification is performed to check timing and designing rules. So finally, the design is converted into GDS2 format and sent to the foundry. This step is called tape out and marks the end of the design phase. So this slide summarizes the complete chip design process. If we talk about the VLSI design flow, why is it important? Then first, it helps convert high-level requirements in a real integrated circuit. Requirements usually begin as documents or customer needs, and structured flow is essential to translate them to reliable into silicon. Secondly, modern ICs are extremely complex. A well-defined design flow helps manage this complexity by keeping the design organized, modular, and easier to maintain. Another major benefit is team collaboration. Chip design involves multiple teams: architecture engineers, then RTL designers, verification engineers, physical design engineers, testing team. A common design flow ensures smooth coordination, synchronization, and clear handoffs between these team members. The design flow also ensures that strict power, performance, and area constraints are met. These parameters are checked at multiple stages to avoid surprises later. Finally, the design flow supports iterative improvement. Issues are detected early and corrected before they become costly, saving time and development efforts. So overall, the VLSI design flow is essential for building reliable and high quality chips. If we look at the main steps of VLSI design flow in a simplified form, then we begin with the specification as mentioned before. In this step, we clearly define the functionality of the IC, including all the trade-offs and of the performance power area, and acts as foundation of the entire design. Next is the design entry. We create a high-level model of the circuit using hardware description languages like Verilog or VHDL. The step focuses on describing the behavior of the circuit rather than its physical implementation. After design entry comes synthesis. A synthesis converts the high-level HDL description into a netlist made up of logic gates and components based on the target technology. And moving further is the verification. Verification ensures the design meets the given specification and behaves correctly. This is done using simulators and other testing techniques to catch errors early. There are simulators such as VCS. There are some simulators by Cadence and Siemens, Synopsys, such companies in the industry. And once the logic design is verified, we proceed to layout, which is part of physical design. In this step, Components are placed on the chip, and routing is done while considering signal integrity, available space, and power distribution. Finally, the design reaches the fabrication stage. Here, the actual integrated circuit is manufactured using semiconductor processes such as photolithography, etching, and doping. So, these steps together describe how VLSI design moves from an idea to a physical silicon chip. Now, let's look at the two main types of VLSI design flow. The first one is the top down design flow. In this approach, the design starts at the system level. We first define what the entire system should do, then gradually break it down into smaller blocks, modules, and finally into transistor level implementation. This method is widely used in industry because it helps us clearly understand the functionality before focusing on low level details. The second approach is the bottom up design flow. Here, the process starts with the basic building blocks such as transistor or small logic cells. These blocks are then combined to form larger modules and eventually a complete system. This approach is useful when optimizing performance, power, or area at a very low level, or when reusable blocks are already available. In practice, most real world designers use a combination of both the approaches: top down planning with bottom up optimization. This diagram again shows the ASIC design flow, which is divided into front end design and back end design. The front end design is the design specification, RTL description, and functional verification. And I work as RTL designer and verification uh, from here to here. So in tomorrow's session, I'll go over very practical example how the entire front end design is being done. Uh, and then comes the back end design engineer, which is divided into logical design and physical design, with synthesis, gate level netlist to placement and route to GDS2. The specification and architecture. So every chip design begins with the concept or requirement driven by market needs, innovation goals, or customer use cases. At this stage, the purpose and functionality of the chip are clearly defined. Detailed specifications are created. These specifications act as blueprint for the entire VLSI design process. Based on the specification, architect define the high-level architecture. The chip is also considered as part of a larger system, ensuring it will integrate correctly with the overall board and system design. And early board designs helps avoid integration issues later in the product life cycle. If I talk about the front-end design overview, then front-end design begins with customer specification. Here we define the chip's functionality and set all the performance, power, and area targets. This stage forms the front-end portion of the RTL to GDS2 flow. Most of the logic behavior of the chip is defined in this phase. And RTL design the register transfer level. Obviously, we implement the specification using Verilog or VHDL. VHDL is good for FPGA flow, and Verilog is okay for simulation. RTL describes how data moves between registers on each clock cycle. This is where FSMs, data paths, and interfaces are implemented. The RTL must be clean, synthesizable, and modular because it serves as the golden reference for all the later stages. The next is functional verification. So, functional verification runs in parallel with the RTL design. The goal is to ensure the RTL behaves exactly as intended by the specification and to catch bugs as early as possible. This is done using test benches, RTL simulator, their coverage checks, assertions, and sometimes formal verification. This is done using a language called UVM, which is the Universal Verification Methodology. This is defined by Accelera as a global language which can be used. Only after the RTL is thoroughly verified, we do move to the synthesis stage. And what is logic synthesis? So, logic synthesis converts the RTL code into a gate level netlist. It maps abstract logic into standard cells from a technology library. This is first stage where the design becomes technology aware. Synthesis also optimizes the design for power, performance, and area, and may insert DFT structures also. STA, the static timing analysis, is also very important. It checks timing correctness without simulation. It ensures setup and hold requirements are met. Pre-layout STA is important because it detects issues before physical design, reducing costly iterations later and guiding RTL and synthesis optimization. So there are chances that there can be setup and hold violation, such as the signal is coming just before the clock edge or the signal is coming after the clock edge. So it causes some kinds of delay, which should be caught and should be analyzed at an early stage. And since not all, uh, and the next is you can say DFT, the design for testability. So a DFT improves the testability of a chip after fabrication. Since not all internal nodes are directly observable, DFT helps detect manufacturing defects, improve test coverage, and reduce post-silicon debug cost. A DFT is critical for high yield and volume production. There can be issues later at the stage, such as the chip can be heated up, or there can be sand particles which can go on and cause issues later. So it's better that we do some kind of DFT techniques earlier itself, such as common DFT techniques include scan insertions with the flip-flops, a scan port, scan chain is inserted, and LBIST and MBIST, which is built-in self-test. And like I mentioned, scan insertion connects flip-flop into scan chains to improve controllability and observability. And LBIST tests logic blocks, while M stands for memory, MBIST tests embedded memories. Moving on to the physical design. So, what is a physical design? Physical design converts the logical netlist into a physical layout. It determines manufacturability, performance, and power forms the backend of the RTL to GDS2 flow. This stage translates gates and nets into actual silicon geometry. And major stages in physical design include design import, floor planning, placement, clock tree synthesis, routing, sign off, and finally GDS2 generation, also known as tape out. Giving you some overview of place and route PNR. PNR takes input like the gate level netlist, constraints, and libraries. It places standard cells, macros, and IO pads, and then routes all connections while meeting timing and design rules. And the output is the final layout database. What are standard cells? These are large functional blocks delivered as a single unit. And these are macros, sorry. And example include SRAMs and CPU cores, etc. And these macro are basically made up of standard cells. Standard cells are pre-designed, pre-verified logic blocks such as AND or NAND or flip-flops or buffers or clock gating logics and IO pads, input-output pads. They connect the internal chip signals to the outside world. Next are the floor planning objectives. Floor planning defines the chip size and shape. It organizes the blocks and macros and aims to minimize wire length and congestion. It also ensures sufficient power distribution, which is critical or reliable operation. And CTS is also very important, which is the clock tree synthesis. The purpose of clock tree synthesis or CTS is to distribute the clock signal uniformly across the design. The main goal is to minimize clock skew and jitter so that all the registers see the clock at nearly the same time. And CTS also helps balance clock latency across registers, which is essential for correct synchronization operation. A well-designed clock tree ensures reliable timing across the chip because as you know that all the components of the chip should get the clock at the same time. So it has some of techniques also to achieve that. And the CTS uses techniques such as clock buffer and inverter uh, insertion. Also, balanced clock structures such as H tree or clock meshes are commonly used to distribute the clock evenly. CTS also supports clock gating, which helps reduce power consumption as it disables the clock where the clock is not needed. Next is routing. Uh, so routing establishes the physical connection between cells on the chip. It uses multiple metal layers and wires to connect signals. The routing stage ensures signal integrity and checks that all connections follow design rule constraints, also known as DRC. So, routing stages is done first, the global routing, which plans approximate paths for connection. It is just the planning stage, and then comes the detailed routing, where the exact wire geometry are created. And after routing, post-route timing analysis is performed to verify timing accuracy. The sign-off checks. Before manufacturing, the design must pass the sign-off checks. These include post-route static timing analysis, the design rule checks, the LVS and IR or the voltage drop, and EM analysis, the electromigration analysis. These checks ensure the design is safe, manufacturable, and reliable. If issues are found during sign-off, engineering change order or ECOs are applied. ECOs fix remaining timing, power, or DRC issues while making minimal changes to the design to avoid disruption. And finally, the GDS2 generation. Once the design passes all these checks, final layout is generated in GDS2 format. GDS2 is nothing but a format. This database contains the complete geometry, layers, and connectivity information. GDS2 is the standard format used by foundries for IC manufacturing. And the final step is tape out. Tape out is the handoff of the final design to the foundry. It marks the end of the design phase and the beginning of fabrication. After tape out, the chip moves into manufacturing. Uh, Moving on to the challenges in VLSI design flow. Now, let's discuss some of the key challenges in the VLSI design flow. One major challenge in the VLSI industry is time to market. There is always pressure to build products faster to meet market demands while still ensuring high quality and reliability. Balancing speed and correctness is not easy. Another challenge is power consumption. Many modern applications require high performance, but power budgets are very tight. Designers must ensure that power does not exceed specified limits, especially for mobile and battery operated devices. The complexity of modern integrated circuits is also a big challenge. Today's chip must operate correctly across different temperatures, voltages, and workloads. Designing systems that work reliably under all these conditions is very difficult. There are also challenges related to physical layout, such as signal in integrity issues, power distribution problem, and routing congestion. As technology scales, these issues become more severe. Finally, achieving a cost-effective solution while meeting performance, power, and area goals is always a challenge. Optimizing all three together, often called the PPA problem, is one of the hardest part of the VLSI design. Looking at some future trends in VLSI design, so one major trend is the increasing use of AI and machine learning in design automation. These techniques help improve efficiency and reduce time to market through better optimization and automation. You can simply give a specification, chip specification to even chat GPT nowadays, and it can just produce the HDL, it can produce the Verilog VHDL for you. It can also, the design rule checks, you can give it to them. It can also produce the STC files for you. So the market is evolving. Another trend is advanced chip packaging. Technologies such as chiplets and 3D integration allow better performance and higher integration without relying only on transistor scaling. New applications in area like IoT, 5G, and artificial intelligence are driving the need for new architecture and design methodologies. There is also a growing focus on improving manufacturing productivity while reducing costs through better tools and processes. Overall, the VLSI design flow is continuously evolving to handle increasingly complexity and new application demands. If I talk about the advantages of a VLSI design flow, then ASIC-based designs are highly power efficient and area efficient, making them ideal for specific applications. They can be optimized for high performance, allowing designs to run at very high speeds. while minimizing processing time. For applications with low power requirements, ASICs are especially suitable. In the long term, ASICs can be cost effective since unnecessary components are eliminated, reducing the overall bill of materials. And finally, a well-defined design flow allows team to adapt to the changing market and technology requirement more efficiently. Along with advantages, there are some limitations of the VLSI design flow, especially for ASICs. ASIC design requires specialized knowledge, tools, and fabrication facilities, which makes it expensive. The overall process from design to fabrication and testing can be time consuming, which may delay product releases. Once an ASIC is fabricated, it is not easy modifiable. So it is not suitable for applications requiring frequent updates. Manufacturing issue such as low yield or defects can lead to costly delays. And finally, the high complexity of the design flow makes it challenging for team without sufficient expertise. Um, Finally, looking at the applications of VLSI design flow, uh, VLSI technology is widely used in consumer electronics such as smartphones, tablets, smartwatches, where functions like wireless connectivity, power management, and signal processing are implemented using ASICs. In networking and telecommunication, VLSI chips are used in switches, routers, and high-speed data processing systems. In the automotive industry, Tesla, you must have heard of, VLSI enables driver assistance systems, engine control, safety features, and information system. VLSI is also used in industries and healthcare system for control, monitoring, and data processing. Most of the surgery these days are done through machines itself, and it will increase in the coming future. Additionally, these systems are critical in defense applications as well, including radar processing, navigation, and secure communication, along with drones also, which is getting a lot of traction and changing the war front these days. So overall, the VLSI design flow plays a crucial role across a wide range of modern technologies. Thank you. I hope by the end of the presentation, uh, now you were aware of the design flow of chip manufacturing.
We now move on to the question and answer session. So participants are requested to post their questions regarding the design flow in the chat box.
We will take 3 to 4 questions to discuss the practical challenges in design verification and physical design.
So if there are some questions from the participant side, feel free to post in the chat box, or you may even raise your hands.
Ma'am, they can't speak, their mics are muted.
They can just raise their hand and we will give them the presenter right.
Ma'am, one question is how flows are monitored and improved.
So various teams are working on it on the flow, and they need to be in sync. There are RTL engineers They are working on the Verilog or the VHDL languages. Now they are giving the RTL code to the verification, and then the verification is verifying that RTL code. And in case of any error, is that is going back to the RTL designer. And then the RTL designer is correcting that in the code and giving it back to the verification engineer. At the same time, the verification engineer is giving that to the software engineer or the firmware engineer. The firmware engineer is further going ahead and then taking that in C language and burning it and testing it on maybe an FPGA board. So a lot of synchronization is needed between the teams. So the flow is obviously managed through proper processes in the companies, and it is improved using various tools. There are various company out there which have tools where there can be a single tool to maybe generate output for all these teams. Like a single tool is there which can generate the RTL Verilog logic. Same tool. So in case there is any issue or any change in the specification, then it is catered to the RTL engineer also. The verification engineer can have one golden single source where it can just simply regenerate the output. This is how there are a lot of tools and companies are coming up to improve the flow because there are a lot of synchronization which is needed.
Ma'am, the
Ma'am, there
next
is
question
one more
is
question. What are the industrial tools used for chip fabrication end,
I'm sorry you
end
were
to end?
breaking off your
Ma'am, there is
network.
one more question. What are the industrial tools used for chip fabrication end to end?
So there is no one tool which is used end to end. There are various companies out there which are giving multiple tools. There are some companies which are focused only on the front end. And as I mentioned, Cadence has Xelium, Synopsys has VCS, and then Siemens has Questa Sim, and Model Sim is there, which students can be used and which is there in all, I guess, all the colleges also. And then there are tools for checking the design checks. The Synopsys has tools to check that. Then there are specific tools to check the clock. Then there are specific tools like within Cadence, there are multiple tools for to cater to the requirement of each stage in the VLSI design flow or the chip flow.
Ma'am, one more question. Can you elaborate UVM?
Uh, UVM is there is one Accelera is a committee which brings out the industry standards. Accelera has like the Verilog, VHDL, and UVM. UVM is um, universal verification methodology. It has various constraints for verifying a chip design. You can have a UVM model like you are creating an RTL model, a register level RTL in Verilog. Now, around that, you can have a verification environment with various components like uh, there are various stimulus which can be given. I am creating a chip for say, an elevator uh, or say a mobile phone. So I will give various negative and positive test to that mobile phone. We will give like to test positive values. Like this particular button, or by clicking on this particular button, following values it can take. So I will give the series those values and the negative testing also. So it is a, you can say, a virtual environment, a software based environment where the RTL test can be tested by giving negative values and positive values and looking at the result through simulation. And there are various simulators, like I mentioned, the model sim or the Questa sim at the industry level, which we use, where you can check that it is following that protocol, following what I specified or not. Is the functionality which I wanted has been achieved or not?
Ma'am, can you explain how static analysis is done?
Static analysis also has its own set of tool which is there in the market to test that. Sometimes it's like digital world works on 0 and 1, but uh, it the value cannot be just 0 and value cannot be just 1. There can be delays. We make a clock as a straight line, but in the practical world, it's a little bit slanting. Like the it there can be delays. There can be something when uh, the clock is coming in a slanting slope. You can imagine. So it causes the setup and hold time delays. So uh, so these needs to be kept in time, that the next clock cycle, how much the next clock cycle to be delayed, so that the signal which was to be received in the previous clock cycle has been received efficiently before the next clock cycle. I hope I was
Ma'am,
able
can
to
you
answer that.
also ma'am, can you also tell us about open source tools? Which tools are available?
You can download the model sim, as I'm saying. You can also have the peak RDL. Peak RDL is something, there's a language for specification. Okay, you are designing your own chip, you have your specification. You can write that in say system RDL, and then you can generate its output in Verilog. You can take that Verilog output onto EDA Playground. EDA Playground is also open source. And then in EDA Playground, you can check its simulation if that Verilog or the UVM code is correct or not. And then uh, that can be further taken um, to the model sim and do the simulation. So at least your front end part is done through open source.
Thank you very much, ma'am, for such an
Ma'am, there is
engaging
one
and
more question. Wait a second. There's one more question. In industry, Verilog or VHDL, which is preferable?
Verilog is preferable. It is more new, it is more fast, it is easy to write, and so Verilog is preferred in the industry.
Okay, ma'am, I think those were all the questions. So
Thank you so much for having me here.
thank you very much, ma'am, for such an engaging and technically detailed session. Your walkthrough of the VLSI design flow provided excellent clarity on industry standard practices.
the transition from RTL to GDS2 is a critical phase in chip production, and your insights have undoubtedly benefited all the researchers and faculty members present here. We are extremely grateful for your time.
Bef- Before we proceed to the next session, we kindly request all participants to take a moment to fill out the feedback form for technical session 7. The feedback link has been shared in the chat box. Your feedback helps us continuously improve the quality of this FDP.
For session 2, our speaker, Mr. Vinay Budraja, will be joining us by 7:30, and the topic of his session is the role of nanomaterials in the next gen semiconductor generation.
We are going to take a small break. In fact, the next session was scheduled at 7:30 as per the exact schedule. So we are taking a break till the next speaker joins. Meanwhile, all participants are requested to fill the feedback forms.
We now proceed to welcome our second speaker for the day. Joining us from the United States, Dr. Vinay Budhraja. Dr. Budhraja is an assistant professor in the Department of Electrical Engineering at Northern Illinois University, USA. He's a distinguished academician with deep expertise in material sciences and electronic devices. His research focuses on advanced materials and their applications in electronic devices. His work pushes the boundaries of what semiconductor devices can achieve through material innovation.
Bringing an academic perspective to our FDP, he will now deliver technical session 8 on nanomaterials and their role in next-gen semiconductor devices. The chat box will remain open and the Q&A session will be taken at the end. We now invite Dr. Vinay Budraja to kindly begin the session.
Hello, everyone. Uh, I think you are able to hear my voice, right?
Yes, sir.
Let
Yes.
me quickly share my screen. Okay, so mhm. Okay, can you guys see my screen?
Yes, sir, we can see your screen.
Okay. Okay, so good evening, everyone, and it's really an honor to give a presentation in this nice event. And this is my second time delivering the talk. So even last year, you organized the session were very well, and it's continuation in the second year. So that's really great, and I'm happy to attend the session and honored to delivering the talk. So I belong to Northern Illinois University, and some of you who are not aware about Northern Illinois University, it's close to Chicago City, which is one of very popular, and you are all aware of it. So most of my work is being done at Microelectronics Research and Development Lab, and about NIU, the engineering program established in 1985, and then in 1995 it moved to the current building uh, with a budget of 45 million through state funding, and NIU MRDL was established through the state funding. Purpose was to develop the workforce development and R&D needs industry startups. So those were the focus of establishing the MRDL labs. And MRDL labs is comprised of 4,200 square feet of clean room space with designated work. So we have three main type of classes. Class 100 clean room, class 1000, class 10,000 clean room. Uh, so we have the facility of thick film processing in class 1000 clean room, semiconductor processing in class 100, analysis lab in class 1000, and thin film processing class 100. And we are open for any collaboration in the future. Some of you who are interested to develop the relationship in semiconductor fabrication and testing, we would be very happy to help. Now I come back to my presentation. Here are the main outlines. This whole discussion is uh, divided into four parts about the nanomaterial. So it starts with the foundations and the motivation. So I'll cover the scope of the nanomaterials, its evolution in semiconductor devices. What are the main fundamental scaling challenges in the adoption of nanomaterials for the development of semiconductor devices? What are the nanomaterials which are being used in semiconductor devices? Why size matter? Because nano, first thing come into mind that is a nano size. Part two has major nanomaterial platforms, which are like carbon nanomaterials, 2D semiconductor, nanowires, quantum dots, and many other. But currently, these four are the major nanomaterial platforms. Uh, Part three covers nanomaterial in next generation devices, which has the advanced transistor architectures, organic electronics in biosensing applications, nanomaterials in memory devices, neuromorphic and AI hardware, sensors and bioelectronics. And then part four is mainly about the outlook and the discussion, which covers the industrial roadmap of semiconductor technology, open research challenges, and finally the summary. Uh, Foundations and the motivation. Uh, scope Scope of nanomaterials in semiconductor devices. We are heavily dependent on CMOS technology because most of the companies like TI, uh, Intel, IBM, they build their microcontrollers, which is the main key device element in most of the electronic devices, is based on the CMOS, and the CMOS scaling needs new material. Uh, and that's why nanomaterials find its scope in semiconductor devices. What nanomaterials bring to the device physics and the device plus system level impact. So figure on the left side, you can see that as the size shrink, you can have more devices per square area. So the density of the components increases. And with the evolution of the year, CMOS scaling, which is being used in flash, DRAM, with the year, you can see it's double. And in the graph of 2010 to 2025, the flash, which is like 2x per years to flash 1 terabyte, and the DRAM has also double in 3 years. Power technologies for next generation semiconductor manufacturing. So we have seen different type of packaging, which moves from chip scale to 3D integrated. So it's evolved from chip scale package, system in package, FinFET, GA, FETs, and the 3D integrated circuits. uh, Evolution of semiconductor devices. It started from planar CMOS to nanostructure devices. So in a planar MOSFET, you can see in this figure, it's a very nice figure being explained over here for the evolution of transistors. In Till 2011, planar FET was being in the development, and the size shrink was continuously happening, and in 2011 it reached to its maximum limit, and then a industry decided that further shrinkage of the size will not further help. So in that case, the technology of FinFET introduced, and the FinFET, which has I'm sorry, Miss Like my health is not very well, but yeah. Um, in source and drain with a common gate, this is a CMOS with the FinFET. So, but it uses the fin, so that's why the name was given as the fin, uh, along with the FET. And then it further evolved to the GAA FET and the CFET, which is mainly the structure. So GAA has the multiple gate, and the CFET, it's on the vertical side. So it was the evolution from Moore's law versus more than a Moore. And this is the prediction, and this figure is being used at many places. Now it's like getting very popular, and this tells about the prediction up to 2039. And uh, so you can see, like, it's if we talk about the FinFET, it's not new. It's like, decade old story, and then it's evolved from FinFET to the nano sheet, which will be dominated from 2025 to 2029, and then further 2031 to 35 CFET, and then 37 and beyond, it will be 2D FETs. Next is the fundamental scaling challenges. Why silicon alone is not enough. Um, our main development was dependent on the silicon, and silicon has its own advantages and the disadvantages. Um, Why it's not enough? Because of the short channel effects, mobility degradation, power density crisis, leakage, and the variability. We discuss these effects one by one. So first is like a short channel effects, leakage, and the power dissipation. So with the evolution of the technology, you can see the power requirements are like increasing, because we are shrinking the size, but at the same time you are increasing the density, and to handle all more components in a same area or in a lesser area, it gives the short channel effect and the leakage and the power dissipation issues, which needs to be handled properly. And the total power dissipation, it has like either in terms of dynamic power or the static power, and it faces different challenges like switching, glitching, and short circuit, drain induced barrier lowering, punch through, sub threshold, gate tunneling, hot carrier injection. So there is a demand for higher mobility, lower power, and flexible and heterogeneous integration. So that cannot be handled by silicon alone. Uh, that's why nanomaterial find its scope in semiconductor devices. So this chart shows the different parameters requirement in 2022 and beyond. Uh, So let's further move on to the nanomaterials. So what nanomaterials are being used? So first, the basic definition means like it should have the dimension below 100 nanometer, and it has a different classification. The materials has different classification based on the dimension of the property. So like some material, they show its property in 0 dimension, in 1 dimension, 2 dimension, and the 3 dimension. 0 dimension materials covers mainly quantum dots, nanoparticles. 1 dimension are like nanowires, nanotubes. 2 dimension graphene and dimetal chalcodonide materials, and 3D are like nano structured, like nanoporous and nanocomposite. 3D are still in the research phase, and at very small level they are being introduced in the commercial one. uh, so this graph shows the classification of the nanomaterials. The quantum dots, they are the nanoparticles which shows the optical effects which tune the band gap, and that is being used in the optical applications. 1 dimension covers like the nanorods, nanowires, and 2 dimension covers the sheets, films, and 3D are like the pillars which are being used for electromechanical systems in the MEMS devices. So 3D is most of the future, like long-term future in 2030 and beyond. We will see the devices will be based on the 3D materials. So these classification of nanomaterials has different morphology, which has like flatness, sphericity, aspect ratio, and based on the aspect ratio, you can make like nanowires, nano zigzags, nano pillars, nanofibers. There are also like low aspect ratio materials exist in form of nanospheres, nanopyramids, nanocubes. And all these materials exist in different state and different chemical composition, which we will cover when we introduce the devices based on that. So why size matters? Size matters because it has the quantum confinement, which is like band gap engineering on demand. And nanomaterials allow band gap tuning without changing chemistry. Quantum dot is one of very good example. It's a size dependent emission, and you can see when it's like exists in the 3D bulk, 2D quantum well, 1D quantum wire, 0D quantum dot, then density of states changes, and density of state control the carrier flow. Okay. Uh, so, due to the quantum confinement, it is being used in optoelectronic applications, low power logic, and biocompatible sensors. Second reason why size matter is the because of the surface dominance when interfaces rule performance. So at nanoscale, interfaces dominate over bulk properties. Okay, so so trap states and surface states dominate transport, and functionalization becomes a device parameter. Functionalization means the how the atoms respond with respect to the biosensing application. So that is in sensor, it's called like functionalization mechanism, and it is perfect for sensing and bioelectronics. Every molecule binding measures electrical change. Okay, so this is like one of very important sentence. Uh, so surface to volume ratio that changes with respect to the nanomaterial, and that has its influence on physical properties of material, influence on catalytic properties of material, and that's visualize the increase in the ratio, and that controls the device operations. Why size matter? The third reason is enhanced electrical transport beyond bulk mobility. Nanomaterials enable ballistic, quasi-ballistic, and low scattering transport, so which controls the mobility in the devices. And carbon nanotubes, graphene, nanowires, those are like good examples of controlling the mobility in the devices. The outcome is it has the faster devices, low power consumption. Mechanical flexibility is another advantage with the nanomaterials. Nanomaterials decouple electrical performance from mechanical rigidity. Why this is revolutionary? Because flexible ICs can be easily fabricated. Wearable and implantable electronics get its application because of the mechanical flexibility, and conformal sensors like skin, leaves, organs. So many times you have seen the devices which are like skin fit or the implanted. So at that time, mechanical flexibility matters. And bulk silicon is brittle, and nanomaterials are the compliant with the mechanical flexibility. Third reason why size matter, it gives extreme sensitivity, like single molecule and single event detection. This is also like long-term outcome. In the coming future, you might have heard the terms like in like 2050, we will have most of the human organs will be the electronic based devices. Suppose like, and it gives really good revolution in the medical field. So people will be able to survive with the synthetic heart, with the artificial different human organs, like even brain as well. So many times the devices which are being attached to the brain, and some experiments have been done on the mice and the rabbits. So currently it's on the research stage, not very much commercial, but in the long run, single molecule and single event detection is even possible. And the range is very, very small, like below 5 nanometers. So it has a lot of challenges which are coming, and it's but its development will be very interesting to to see its performance in the biomedical field. But mechanism, it covers the field effect modulation, which is the field effect transfer effect on the semiconductor devices. That's due to the carrier transport. But in the case of single molecule, it will be mainly based on the interface states, and surface charge gets affected. Volumetric doping in OECD is another example. We'll cover that because my current research is based on the OECD. So some slides I will cover the OECD part. This has the great lead in the development of semiconductor devices. That's why nanomaterials dominate in biosensors, where silicon has its own limitations. Now, part two, this covers major nanomaterial platform, and first one is the carbon-based nanomaterials. Two major players are carbon nanotube and the graphene. So you all are aware of the MOSFET structure, right? Which has like source, drain, gate, and the oxide, gate oxide. So the semiconductor you use in traditional MOSFET, that has the bulk semiconductor you use, right? And in the nanomaterial based FET, you replace that semiconductor with the thin films. And this example shows the semiconductor portion is being controlled through the carbon nanotube. Industry note, the carbon nanotube based CPUs, they have been introduced and are perfectly being used in many different CPU operations, and that has the higher speed and lower switching time. So advantage with the carbon nanotube FETs, it has the near ballistic transport, excellent subthreshold slope, low power logic. Carbon nanotube based FET, they exist in three form: top gate, bottom gate, coaxial gate. So top gate means the gate is on the top portion. So it starts with the development of carbon nanotube, and then you make the source drain contact, and then on top of it you make the gate dielectric, and then you deposit the top gate, which is regular metal. So this has the gate which is on the top gate, and the semiconductor, which is the carbon nanotube, that is in the thin film form. In the case of bottom gate, the gate is on the bottom. You can see the side view of the device of the bottom gate. So it has a silicon substrate, and then on top of it, silicon dioxide insulator, carbon nanotube film is being further deposited, and then source and drain. That is the bottom gate. Coaxial gate, this is like the future technology. So in the case of coaxial, uh, all the source, drain, and the gate, they are coaxial. So they are in the circular portion, and the carbon nanotube is being deposited in the cylindrical form, because carbon nanotubes in the nanometer range, they are already in the cylindrical form, right? So that's why the name is given as the tubes, like nanotubes. So across those nanotubes, you can deposit the gate and the dielectric around it, and complete the carbon nanotube based FET. So that is coaxial gate. Coaxial gate has lot of advantages because it has like size shrinkage, and in the single molecule based sensing, it's being used. But the fabrication is complicated, so it's still under the research phase. How carbon nanotubes work. So this graph shows the comparison between standard MOSFET and the carbon nanotube based FET. Uh, in the standard MOSFET, you can see between source and drain, when you flow the when you apply the voltage, how the band diagram being drawn between source and drain. uh, in the operation, you can see that it's like electron, they have to move from source to drain when we apply the drain to source voltage. And in the linear region, the device turns on, and here is the banding. But in the case of carbon nanotube, you can see like it has like no more flat between source to drain, so carriers can easily flow between source to drain. So that has the advantage over traditional MOSFET, so it increases the speed. The current is being controlled in standard MOSFET. You are aware of this, like a standard formula, where drain current is dependent on the mobility, the ratio of width to length, and the C oxide. But in the case of carbon nanotube, because the size shrinkage, and you can see that the density of state changes with respect to the size, so that is being reflected in the estimation of the drain current. So it dependent on the charge in the channel, transmission and the contact, and the bias dependence, carrier injection between source to drain. So the advantage is it doesn't have any spatial dependence and no mobility dependence. Next category of carbon nanotube, carbon nanomaterial based FETs, that is graphene. FETs is a 2D material, and it has its own advantages like zero band gap, exceptional mobility, and thermal conductivity. This is being used in RF electronics interconnects and the uh, sensor based applications. Uh, and the graph, you can see how the drain current varies with respect to the drain to source voltage. And so here you can see, because the device sizes are so small, and um, the device turns on very fast, so that's why like saturation sometimes is missing in the graphene based FET. But it has its own advantage, that it has very high on to off ratio. and that's being reflected in subthreshold slope. Graphene-based FETs, they find very nice applications in the biosensing. Here you can see the graphene FET-based biomarkers. They are being used in many different disease detections, such as like HIV, prostate cancer, Alzheimer, breast, lung cancer, malignant tumors, and carcinoma. uh, so graphene-based FETs, because the sizes are very small, and it has a low power advantages, and the switching speed is very fast. So graphene-based FET are ideal candidate for biosensing applications, especially where the signal strength is very, very low. Next category of the nanomaterials platforms is 2D semiconductor. Uh, the possible materials are MoS2, WS2, WSC2, like molybdenum and antimony-based devices. So they show the 2D semiconducting properties. Means like in different dimensions, it has different carrier transport and the charge concentration. Here is the side view of MoS2 based FETs. So on top of the SiO2, a small layer of MoS2 is being deposited, and then it completes its MOSFET base structure. Uh, and it has the advantage like intrinsic band gap lies between 1 to 2 electron volt, and it has atomic scale thickness, and it has very good gate control. These are ideal for ultra skilled FET, flexible and variable electronics. Uh, the band diagram you can see very much similar to the carbon nanotube, as we saw earlier in the on state and the off state. And even device sizes are small. You can see proper saturation region even at lower drain to source voltages. A device physics of 2D FETs, you can have these materials being deposited on ultra thin body, and it has reduced short channel effects. It has interface dominance. And in the figure, you can see like the MOS2 based wafers are available on the glass and on the plastic sheets. Uh, they are ideal for the transparent and easily compatible on the plastic and the low temperature substrate. Flexible and variable applications like bending tolerance, low temperature processing, printed electronics compatibility are available with MOS2. Now, MOS2, they are also possible with the solution processable. So that gives the low temperature advantages. One of the example is the biomarker of bladder cancer in urine. Uh, in one of that application, MOS2 FET arrays were being used, uh, and uh, um, and you can see that it control the CK8 detection, which is one of the biomarker in the bladder cancer. In the case of bladder cancer, uh, with the carbon nanotube, with updating Y2O3, it's like a wet device in the microfluidics, and that's also being used in the cancer biomarkers. Next type of materials in the nanomaterial platform are semiconductor nanowires. And this is like more commercial than the earlier carbon nanotubes and the graphene-based FETs. The reasons are that they are using the commercial base materials such as silicon, germanium, indium arsenide, and the gallium nitride, which are being dominant for the last more than 100 years. So that's why, like anything, like you are finding alternative of the silicon, but in some case, if you have to use with the silicon, you always prefer, and it's easily being developed. So that has the reason why, like semiconductor nanowires, they are dominant over the carbon nanotube and the graphene FETs. So three structure, like planar structure and the fin, and then the gate all around. You can see, like multiple nano sheets. So gate all around geometry is the future. So it has superior electrostatic control. It's ideal for sub 5 nanometer nodes. Applications, logic transistors, photodetectors, and the energy harvesting, which are like main of our core requirements, because in computers and cell phone in our daily life, we are heavily dependent on these things. Uh, what makes them special? Uh, you can control the size, so they are like size tunable band gap. It has discrete energy levels, uh, and you can see it has different energy levels, and with the decreasing size, the different energy levels are being available, and the tune, and it has a changes in the optical properties. So you can see the normal intensity of the wavelength that changes with the size. So the band gap can be tuned with respect to the size. Okay, actually, means like from here means like it's a quantum dot base. I'm talking about the quantum dot base FETs. Quantum dot base FETs, they are being used in non-volatile memory and display and optoelectronics. So you can see that between source to drain, uh, the quantum dots, they are being used as a semiconducting thin film layer, and the size shrinkage is possible by controlling the size of the quantum dots. Next category is the organic nanomaterials. Uh, what are the organic nanomaterials? They are pi conjugated polymers and small molecule with nanoscale morphology. Examples are P.PSS, polythiophene, donor receptor polymers, and it has charge transport via mixed ionic electronic conduction. They are game changer because they are like soft and mechanical compliant, chemically functionalizable, volumetric conduction, low temperature solution processable. Just looking, okay. Yeah. Some of these organic nanomaterial based devices we will cover in part three. Actually, this is my like core research area, so I am including some of my research results as well in the working of the organic nanomaterial based devices. So with the organic electronics, again, like it's a low temperature processing, and in biosensing applications, they are the ideal candidate. It has weight, size, and also the cost advantages. Now I come to part three, which is the nanomaterials in next gen devices. So in the next generation, the advanced transistor architectures are being required, and FinFET, although like at the university level, FinFET, the fabrication of it is still challenging, but at the industrial level, FinFET is again now getting obsolete. So in the future requirements, we need gate all around and the nanosheet FETs, vertical nanowires FETs. So the figure you can see, like in the FinFET, we have a gate, source, and drain. And by this way, we can have only one source and drain. And with the nanosheet FET, we have the advantage to have different nanosheets in the vertical direction, and that's how like you can control the CMOS technology with one gate, and that's why the name is given as gate all around. So gate all around those nanosheets. The role of nanomaterials is like channel material replacement. It has the interface engineering and low resistance contacts. This figure further shows the distinction between the planar FET to the stack nanosheet. So planar FET, that so in the roadmap uh, before 2011, the planar FETs were the standard. Okay, and then in 2011, FinFET was introduced, and it's further helped to reduce the sizes, and it has better control and prevents the current leakage. Uh, and in the nanosheet, the gate completely surround the channel regions to give even better control than FinFET. So this is also like the roadmap. So it's a past, present, and future. Next part, I would like to cover the organic electronics in the advanced sensing. And now, like some of these are my research results coming from my research lab. And organic thin film transistor is one of the device. So OTFTs are miniaturized devices based upon the electronic responses of organic semiconductor. It has the practical realization of active matrix, OLED, using OTFT requires implementation of low voltage. Pentacene TFT is being shown in this figure. So pentacene is the organic semiconductor we use over here. So it's a gate which is aluminum, and the PMA AL203 is a composite, and the gold is the source and drain. So it started with the deposition of the aluminum gate, and then from the anodization method, we make the gate dielectric. But with the AL203, it has the structure is the porous, and it has the pore holes in the AL203 to get the smoother surface. We planarize with the PMMA by doing the spin coating, and then we do the pentacene from the evaporation technique on top of it. So pentacene is the organic semiconductor which shows p-type semiconducting property, and that control the operation of OTFT. Other candidate for organic semiconductors are like pentacene, DNA, TPA, P3HT, PD, BT. So in the organic semiconductors, both N and P type of organic semiconductors are available to make organic electronic devices. So with the time, it is this area is also evoluting and giving us more flexibility and more materials available to make organic electronic devices. Then after pentacene, source, drain are being deposited from the gold, and flexible and rollable devices were fabricated. And this graph shows the transfer characteristics. We estimated the mobility 0.14 and the threshold minus 8.3. And this device works same as the depletion mode or depletion mode MOSFET. This shows the output characteristic. Next type of organic electronic device is organic electrochemical transistor. Uh, So this device is based on P.PSS, and P.PSS also come under the category of the nanomaterial, and it's being used in many different biosensing applications and has very wide range. So in among other organic semiconductors, you will see most of the cases and most of the sensing applications. In most of the sensing applications, P.PSS is being used. Uh, so here is the basic device structure. So you are all aware of the MOSFET. So in a MOSFET, when you replace the oxide with the electrolyte, so this figure you can see, uh, in the MOSFET, we have metal oxide semiconductor. And in the structure of the MOSFET, if you replace the oxide completely with the electrolyte, you make the OECT. Uh, Here is a short animation how the OECT work. So when we apply the voltage between gate and source across the electrolyte consists of positive and negative ions, right? And when you apply the voltage, it has separation of ions like this, and those separation of ions de-dope the semiconductor channel. And when we apply the voltage between drain to source, it has the flow of carrier between source to drain. And that's how it gives the current. Fabrication flow of the OECT, we use the screen printing technique. And here we use AGCL to make the side gate OECT. So in first figure, you can see it shows the source, drain, and the gate region. We do it from the screen printing. On top of it, we do the P.PSS. For the P.PSS, we again uh, use screen printing. So we have tried P.PSS from 3 different techniques. Uh, One is the drop casting, another is screen printing, and the third one is the spin coating. Out of those three, screen printed works better than other 2 techniques. And then on top of it, we do the electrolyte. And the electrolyte, in this case, we are using the PSSNA base electrolyte. And then we cover the source drain region to avoid the short circuit between gate to source. That completes the OECT devices. These devices are wet devices, and that is the big advantage uh, of OECT in many different sensing applications, because if you want to use any device for the cancer biomarker, you need very fast reaction. And many times we have heard the term that if the cancer was detected in the initial stage, it could be better. So with the help of OECT, it is possible. So those cancer cells, when they are in very small concentration in the body, they will have fast reaction rate with the electrolyte, and that can be detected in the cancer biomarker detection. Uh, we fabricated these devices with 2 different channel lengths, 4 nanometer and 2 nanometer, 4 millimeter and 2 millimeter at the at the first stage. And we uh, we are like reducing its size up to 100 microns, and every time, like, no, we use different mask, and that will be our future work. uh, OECT, about the OECT devices, I would say these are like very new devices, because its history start from 2008. So in comparison to other, it is really a newer device. Uh, so this shows the fabricated structure of the OECT, and the SEM images shows the screen printed layers P.PSS and the interface of P.PSS. PSS. So when there's a reaction rate of the electrolyte with the affected cells, the interface of P dot PSS with the silver that changes. Actually, this I forgot to include one short animation. Uh, Let me do one thing. Um, Okay. Okay. So here are the transistor characteristics uh, of the OECD, like the output and output characteristic. And with respect to channel length, it has the changes in the drain current. And the advantage of this OECD is that it has very, very high transconductance. And that's the advantage of OECD over the MOSFET. uh, so in the traditional MOSFET, you see that there's a oxide between gate to the channel, and the control operation over there is the electrostatic way. When you apply the voltage between gate to source, the charge they collected around gate and the semiconductor is due to the electrostatic manner. And in the case of OECD, it's volumetric capacitance base, because when you apply the voltage between gate to source, instead of having the charge electrostatically separated, they are being separated due to the electric field. And the charge in the case of OECD can easily travel between gate to the semiconductor through the electrolyte. And here is one short animation we have taken from our testing results, or you can say short video. So when we apply the voltage, so you can see there is a bubble formation due to the voltage, and that shows the sensing functionalization at the interface of the electrolyte and the semiconductor. So the drop of the drop of the liquid is the electrolyte, and with the voltage, you can see it has a bubble formation. Is another. See, it has a bubble formation. This shows the functionalization mechanism at the interface of the electrolyte and the semiconductor channel. The blue region is the P dot PSS layer. Uh, Equivalent circuit model of OECD. Uh, Around the electrolyte, it has two different type of capacitances. One is the gate capacitance between a gate to the electrolyte, and there's a channel capacitance between uh, electrolyte to the semiconductor channel. Different type of OECTs can be fabricated. Uh, so this figure shows the different configurations of the OECT. Um, Top gated. In the top gated, we have the source, drain, and the electrolyte, and the gate is the floating gate. It can be like AG, AGCL, where redox potential is the minimum, and the side gated, the coplanar gated means like source, drain, and gate are the coplanar. I would call my devices comes under the category of the coplanar. Uh, vertical OECD. That's another advantage of the OECD, that you can have source and drain on the vertical direction. And this is being used in the neuromorphic applications quite well. Uh, Another type of configuration is the fiber base OECD. The fiber now, like OECTs can be easily fabricated on the fibers, and so it can be easily applicable for the biosensing application, especially for the wound monitoring and the wound healing. In one of the work of the OECD, uh, this has been used in the memory applications where the size of the channel is in few microns, and uh, the OECD, the requirement is that one has to make the solid electrolyte. uh, right now, these devices are wet devices, and the requirement is if we can move towards the dry, and so that it can be used in the memory devices, memory applications, neuromorphic computing, and that is possible if you use a solid electrolyte. And the inks, the screen printed inks, they are, yeah, available. And after screen printing, it get dry, so it's like a jelly form, like a gel. And with the evolution of the technology, we will see in another decade that the more solid electrolytes will be available for the OECTs. Next, in the future generation of the nanomaterials, it is in the memory devices, which cover the resistive RAM, phase change memory, ferroelectric nanostructures. So why memory need nanomaterials? Because conventional flash faces scaling, endurance, and speed limits. Emerging memories rely on nanoscale and nanomaterials, enable non-volatility, fast switching, and the low power. That's why we need nanomaterials in memory. We cover each of this one by one. First is resistive random access memory. Operating principle, it's based on formation of nanoscale conductive filaments, typically in oxide nanomaterials, uh, uh, like HFO2, TiO2, TU2O5, and the filaments for the fabrication available in 1 to 10 nanometer ranges. Uh, Switching is governed by atomic scale oxygen vacancy, and it gives rise to lower switching energy, higher density, faster operation. Uh, Key advantages are metal, insulator metal structure is possible, CMOS structure is possible, and the most important, it's ideal for neuromorphic computing. So neuromorphic computing is the future in the coming decade, and it's not in the very commercial state, and the develop and research is going on, uh, but the demand is huge. Next is the phase change memory. It uses chalconite switching between amorphous and the crystalline. Amorphous gives rise to high resistance, crystalline gives low resistance. The role of nanomaterial is confined nano volume. It gives rise to switching current, power consumption, faster phase transition due to localized Joule heating. Uh, it has endurance to flash, and already Intel Optane has used the phase change memory, and the multi-level cell compatibility is possible with the phase change memory. The third one is the ferroelectric memory. It's based on the polarization, and modern FERAM uses nanoscale HFO2 based ferroelectrics. It emerges at specific nanometer thickness, compatible with CMOS. Uh, it enables the FETs. Key advantages: ultra low power, fast switching, non-volatile with high endurance. Uh, Applications: embedded memory, AI accelerators, edge computing. Next part is the neuromorphic and AI hardwares. The main elements of the neuromorphic computing is the memristors, synaptic devices, brain-inspired computing, and conventional AI hardware falls short because it has the bottleneck. It separates the memory and the processing. It needs high data movement, which has the energy inefficiency and brain-like computation. Uh, if the brain-like computation is required, it needs co-located memory and the processing. The artificial neural network uses the FET development, and it has a functionalization layer along with the channel, and it needs the artificial synapses. So artificial synapses, which is the gate that needs the high computation, like a brain inspired computing. And we we cover these elements one by one. So first one is the memristor, which is a two terminal device which is dependent on the resistance set by nanoscale physical states like conductive filaments, phase distribution, ion migration. uh, and the nanomaterials plays major role because filament width exists between 1 to 10 nanometer. It enables continuous weight advantage, and direct mapping to synaptic weights is possible. Second element of the neuromorphic hardware is the synaptic devices. Synaptic are like the biological based devices. It's like synapses strengthen or weaken via plasticity. It has the ionic drift in oxides, uh, and it's these are like ferroelectric domain switching and phase fraction modulation. The figure shows the biological synapses, and it's being attached to the biological neural network. Uh, Key function are long-term potential and long-term depression, spike timing dependent plasticity. So the response time is required further to be higher. So that is possible with the neuromorphic computing, and it's compute like the brain. So that's why the name is given as a neuromorphic. Why organic and ionic nanomaterials shine? Because it gives natural ion transport, soft and analogous responses, low voltage operation. The devices I discussed from my research, the OECTs are also like good candidate for the neuromorphic computing, and few research groups are working on the neuromorphic computing with the OECT, and it's still in the research phase, but promising for the future. Third element of the neuromorphic computing is the brain-inspired computing architectures. So memristors arranged in nanoscale crossbar perform VMM in one step. So this is revolutionary because it has massive parallelism, order of magnitude lower energy per operation, scales with the device density. Uh, it's emerging in spiking neural networks, memory computing, and edge AI hardware. The neurotransmitter based on UV treated chart trapping. So this is one of the example of MOTE2 based devices. So here you can see the MOTE2 is the receptor which react with the bioelement for the biosensing applications, and rest of the structure looks same as the MOSFET, and there's a resistance between uh, two electrodes, and the receptor is in between. So it shows the pre-synaptic spike. So this figure shows the Raman shift uh, of MOTE2 material. Uh, so, Another figure, that figure D, is action potential, the new neurotransmitter and the receptor. Uh, so shape shows like a brain structure of the human body. So because it compute in that range, uh, that's why the name is given as the neuromorphic computing. And this area is new, further need to be explored. I think like it may be new for many of you, and but it is worth to move into that because this is the coming future. Uh, why nanomaterials are ideal for sensors and the bioelectronics? They need extremely high surface to volume ratio. It has strong surface charge interaction, which is the functionalization mechanism. It has the ability to transduce chemical biological events in terms of the electrical signal. So biological events means the biological interaction between between the biomarker and the bioreceptor that changes the electrical signal that is being reflected in the current response, uh, such as the drain current in the case of OECT, and that changes the transconductance. It has a compatibility with flexible, soft, and low power electronics. I cover some of nice applications of this technology. So one in the kidney transplant. So you can see like the different type of sensors, like the temperature sensors and pressure and other OECT based sensors. They are being done on the same substrate, and uh, study was done on the mice, and the signal response was noticed, and the device sizes was in like few microns. Uh, uh, so the figure that shows with respect to the time, the temperature of the kidney that was being noticed with respect to the time, and it gives the variation in the graph. So that was really nice, and that compared with the main body temperature of the mice. Second is in the cardiovascular monitoring. uh, Here you can see the sensor arrays that was like impedance based sensors. So that changes the impedance response. That's being reflected in the Nyquist plot with respect to the frequency, and uh, the circuit is the LCR meter made up of the organic compounds, and the sensor was being fabricated from the organic materials and uh, being used in the biomedical applications, mainly for the cardiovascular monitoring. Neurological monitoring, uh, again, like for the biosensing applications, they are not very in the very commercial stage at this time. They are like in the growth stage. So most of the tests are being done on mice, rabbit, uh, uh, and in some cases this is like on the pig heart, because that okay, so not the pig, there's a rabbit, but on the pig also the study has been done. So mainly on the animals. Neurological monitoring. So this shows the ICP sensor being attached to the mice, uh, and it's being attached on the brain of the mice to monitor the neurological signal. And these tests are very highly delicate, and the signal strength is very low. So to detect that and doing that study is really very, very complicated. But the future is promising, and it has huge impact in the coming future. Next example for the biosensing is the microfluidics, and this became very common. One thing you might have noticed during the COVID time, they take the blood sample, and within few minutes you can tell whether you are affected or not. So that's possible with the help of the microfluidic interaction. Uh, so here's a graph that shows the microfluidic channel for the Alzheimer diseases, and the OECT arrays are being used over here. Uh, so source, drain, and the semiconductor, those are common. With respect to different applications, only thing changes is the electrolyte. So different applications uses different electrolytes. Here is another test where you can monitor the glucose and and give you information about other body temperature based on the saliva. So you make your OECT and then you take the sample of the saliva from the human saliva. You can detect different diseases. Here is another example of like finger powered microfluidics. So it takes like the invasive way of taking the blood sample. So on a one substrate, you can monitor the glucose, cholesterol, lactate, and the controller. So this graph shows like the glucose, lactate, and cholesterol are being tested at a time. So three things can be tested from one drop of the blood. So that is possible with the microfluidic operations. This is the OECD based the glucose sensor. Again, it's a simple structure based on the microfluidics, and people have taken samples from like saliva, uh, uh, saliva. You can take sample from saliva, urine, or sometimes sweat as well, human sweat. That gives rise to different detection mechanisms, and they are being quite used uh, in many different applications. And you can find many articles in the literature where people have made devices uh, by taking samples invasive and non-invasive way. Difference between invasive and non-invasive means like every time it takes the blood sample is the invasive, and the non-invasive means like you do not need to take like the blood sample at a time, so you can work perfectly with this saliva, urine, or the human sweat. Uh, Now the last part is the outlook and the discussion. So industry roadmap, why the industry need a new roadmap? Because classical Moore law scaling is slowing down. Performance gains now come from integration, architecture, and materials innovation. Nanomaterials are being adopted selectively, not as full replacement for silicon. We cover these points one by one. Here's a Moore's law. So transistor density growth no longer delivers proportional performance gain. Uh, it has the advanced nodes with respect to 3 nanometer, 2 nanometer that comes with the exponential cost increases. This Moore's law, you can see the graph that's rising, 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 and with the time it's like moving towards the stabilization, and that stability gives rise to the demand of the nanomaterial. Performance today is achieved by pulling multiple layers at the same time, not just shrinking the transistor. So this is another important point. The Moore's law, when it started, like when we see like 20 years back, we call it that it is mainly like you shrink the size and then you follow the trend of the Moore's law. But as you shrink the size and the technology, when it goes below the 45 nanometer, the leakage was another challenge with the shrinkage. So it came to the mind that shrinkage is still not possible because you have to handle a lot of leakage. In hypothetical case, you can say, okay, we'll make like 10 nanometer and 1 nanometer and the molecular level. I remember if we go like 20 years back, people were giving the hypothesis that in 2030 or 2050 we will be making the atomic scale devices because they had in mind only the shrinkage they had in the mind. but they were ignoring the leakage. So that's why uh, uh, the performance is achieved by pulling multiple levers at the same time, not just shrinking the transistors. So So this graph shows the evolution of the analog and the passive HV power sensor actuators. So it has the combining SOC and the SIP, the information processing, interacting with people. So non-digital element system in chip, system in package, and system on chip. So that needs a proper balance. Uh, Main takeaway points from here are the integration, architecture, and the materials innovation. Scaling moves from devices to system. So that has the 3D ICs, logic, and the chiplets. Uh, so the impact is reduced data management, higher bandwidth, and the lower energy. Architecture, the compute is redefined around workloads. Impact is order of magnitude, energy efficiency gains. Material innovation, which means like new physics enable new functions. We have seen in previous slides that uh, in the case of like ferroelectric RRAM 2D organ nanomaterial, with the silicon alone, we cannot work with that. So it needs give rise to many different new materials, and that gives scope to the nanomaterials. Uh, the impact of the material innovation is functionality beyond CMOS limitations. Okay, next part is the open research challenges. Uh, the open research challenges with the adoption of nanomaterials are wafer scale synthesis, electrical context, standards, reliability, and the variability. Why these challenges matter? Because nanomaterials show exceptional lab scale performance, and manufacturing reliability and ecosystem gap limit the large scale adoption. These challenges define the future. And so we discuss these challenges one by one. First is the wafer scale synthesis from flakes to the fab. The challenge is that many nanomaterials are demonstrated on small flakes, lab scale substrate, and industry requires 200 to 300 millimeter wafer scale. Means like with the silicon, you can easily produce the wafers of 200 to 300 nanometer, but with the graphene and carbon nanotube and many different nanomaterials, they are mainly like thin film base. Okay, but the requirement is that you have to produce the wafer, and not only the wafer, it's a high quality wafer which has high lifetime and high diffusion length, which is challenges with the nanomaterials. Uh, Key issues are non-uniform growth, grain boundaries and defects, and transfer-related contamination for 2D materials. So the crystallinity is a big challenge. Plus, like nanomaterials, in some cases, the material cost is very high. So producing wafers, and you have to like develop the process like Chakralski is challenging with the nanomaterial to make the substrate. uh, why it's so critical, why we need wafers, because without wafer scale uniformity, nanomaterials cannot enter high volume manufacturing. Next is the electrical context. It is the silent performance killer. The challenge is contact resistance dominate at the nanoscale. When you shrink the size, the contact resistance uh, is highly affected at the interfaces such as the semiconductor, dielectric, and semiconductor metal, and the metal nanomaterial interfaces are poorly understood. The root causes are Fermi level pinning, Schottky barriers, interface contamination, and the damage, which has the consequences. It has the mass intrinsic mobility, reduced switching speed, and increases the variability. So when we adopt the nanomaterials, we see all the positive things, which is good, but at the same time, it has the challenges, and the contact resistance is really one of the big challenge with the nanomaterials. Many times you fabricate these devices, and the stability of the devices is is really challenging. When you make, like, multiple device arrays, many times you will see the device performance are not like very uniform, and it has many different parameters. So the fabrication is really complicated, especially with the nanomaterials, and the uniformity of the thin film layer is another challenge. So that reflect in the contact resistance at different interfaces. Uh, Standards, reliability, and the variability, from scientific novelty to engineer technology, in the adoption of nanomaterials, like material characterization, device benchmarking, and the reliability testing are missing. So the open questions are: how do device age? How stable are interfaces? How reproducible are properties across labs? Uh, and it's like depend on the applications. If I take the example of the organic materials, they are nicely used in the biosensing applications, but the organic compounds are not stable. So that is really one challenge. And even with doing the proper interfacing and the packaging, it is still the device age is not improved. Um, so that's the challenge with the adoption of the organic based nanomaterials. Other nanomaterials, such as like in the carbon nanotubes, the graphene, you can say they are like more uh, stable than the organic base, but they have their own limitations. The growing of those nanomaterials, they don't show the stable performance, especially at the interfaces. So how reproducible the properties are, that is the open question. Next thing is the summary of the discussion. So nanomaterials are not replacement for silicon, they are enablers. They introduce new physical mechanisms like ionic ferroelectric quantum interfacial that extends semiconductor functionality beyond CMOS scaling limits. Uh, Actually, our life is heavily dependent on CMOS, and the CMOS scaling. Uh, the CMOS scaling is the first thing come in our mind, because we use the cell phones, our tablets, our personal computers. Those are our like major requirement. And over there, how good nanomaterials to replace, that is the question. And They can be used along with the silicon, but completely replace silicon is still challenging. Uh, and this graph shows, like, the technology evolved from the planar FET to CFET. But when it needs the demand in the future, at that time you have to integrate the nanomaterials along with the silicon, because silicon has the stability, but the shrinkage is challenging with silicon, and with the nanomaterials it's not an issue. So both technologies has to work in integration. That is like, again, like one of my take. And if one can replace completely other, that doesn't look promising at this time. although both has its own advantages and the disadvantages. Next thing is the performance gains now come from the system level innovation. So the future improvements are driven by the combined impact of the integration, which is like 3D ICs is one of the good example where they use a heterogeneous stacking chiplets. Uh, and the three in the earlier slides as well, we have seen the roadmap of the ITRS in the 2030 or 2030 and beyond. All CMOS technologies will be completely replaced by the 3D. And the 3D heterogeneous stacking, you have to introduce the nanomaterials. The architecture, such as like in-memory computing, neuromorphic, AI accelerators, it gives rise to the nanomaterials, especially the 2D materials, oxides, ferroelectrics, and the organics. Uh, they will be the key role player. And the memory and AI are the earliest success stories in the RAM, like PCM and the ferroelectric memories already exploit nanoscale physics. Memory chip and synaptic devices enable energy efficient AI hardware. So that is really exciting. This graph shows the wheel of the workforce development. So from like chips to chiplets and the foundation ecosystem. Um, the neuromorphic computing, especially with the memories, nanoscale physics give rise to some hope of the nanomaterials. Industry is moving toward the hybrid systems. The roadmap favors hybrid silicon plus nanomaterial, as I already mentioned. 3D integration is being used like 2030 and beyond. Chiplet-based architectures is also the future. So the future chip is a system of materials, not a single material. So that is the takeaway point from today's presentation. Critical challenges remain and define future research in the wafer scale synthesis, contact engineering, reliability standards. So the scientific readiness exists. The engineering readiness is the frontier. The wafer scale synthesis uh, is one of the primary demand from the nanomaterials. So along with the nanomaterials, it's really challenging. So in the integration with the silicon, it gives hope to to this technology. And reliability and standards are critical challenges that will still remain with the nanomaterials for another decade. So here I end my presentation. So here is my like research group. So currently I have like 10 students working and Alejandro and Fayan, I mentioned their name because they are being involved in the fabrication of the OECT, and our future is moving towards the 100 micrometer channel length in the OECT. That's all about details of my group. So I thank you all for giving me the invitation for the presentation. Thanks to the organizers. Now I'm open for the questions. Thank you.
Thank you,
We now
Dr.
invite
Dudraja, for
participants.
such a profound and well-structured session. Your insights into the capabilities of nanomaterials have truly expanded our understanding of what lies beyond conventional silicon limits.
We are highly thankful for your dedication and continued support to this FDP program, and we deeply appreciate your commitment to learning. Thank you, sir.
We now invite participants to post their questions in the chat box.
Sir, the first question is that what is the current status regarding the stability of organic TFTs?
Okay. Yeah. So organic TFT is being now commercially used, and some polymer-based TFTs are being introduced in the market. And in the flat panel displays, you will see two key players who are selling their product So stability wise, if you make it with the organic materials, you have to probably properly passivate it. So and in the sensing applications, uh, many time you are using it for invasive and non-invasive sensing applications. So over there, uh, you can easily work with those devices, especially with the organic one, for up to a month to 60 days.
So the next
And
question
sir,
is, what makes the nanomaterials stubborn on leakage issue than traditional silicon?
Hmm. Okay, so that's a very good question, I would say. The nanomaterials really overcome the leakage because nanomaterials, they are stable in the nanoscale. So when you go to the wafer scale, it has its limitation, but in the nanoscale, it is really promising because, like you see the carbon nanotubes in the shrinkage size uh, within 1 to 10 nanometer, it shows its semiconducting properties very well. So you can see the comparison between multi-wall carbon nanotube versus single wall carbon nanotube, especially with the graphene as well, the single sheet of the graphene. So as the size shrinkage, when you have the demand between 1 to 10 nanometer, leakages are very better controlled with the nanomaterials rather than the silicon.
So what is the difference between neuromorphic and in-memory computing?
Okay, that's like that's the field also I'm exploring. So neuromorphing is really new for me. The devices I'm working on, OECT, the vertical OECTs, they are uh, uh, they are having applications in the neuromorphic. So in the in memory computing, you use the memory devices for the computing applications, but for the neuromorphic, you make the devices itself, such as the FETs and the OECTs, uh, which does its computation very, very fast, which gives the fast switching speed. So that's the main difference between the in-memory computing and the neuromorphic.
so one more question.
Also,
Can you provide the details that what kind of 2D materials that are used in dielectric stack along with gate metal gives high reliability, performance, improved radiation hardening, and gate leakage current control for memory device structure?
This is very complicated question, but yeah. So MOS2 based materials, they use their own dielectric. So in one of the cases, I think I have shared the MOTE2 base. Let me share the screen once again. And here you have seen one case of the MOTE2. In the case of the neuromorphic computing, uh, yeah, here is the case. So, in the case of MOT2, mainly with the molybdenum, the advantage with the molybdenum is that the molybdenum base compounds are available both in the semiconductor form and in the oxide form, and the interface of oxide with the semiconductor in that case is really perfect. So that if I have to choose, I will choose the molybdenum-based 2D semiconductor. And in one of other case, uh, I showed the device structure. uh, where you might have noticed that I showed the molybdenum-based semiconductor along with the molybdenum oxide. So here, MOS2 and the MOX. So here you can see that it is like having the same. Uh, See what the advantage with the silicon. The main advantage of the silicon is that like you use the high temperature techniques to make like silicon dioxide, and the interface of silicon dioxide is very, very good. Uh, so same thing could be applied with the 2D material. If I have to select one of it, I would go with the molybdenum sulfide. So this is one of the ideal candidate. And neuromorphic computing is really tricky. It's like, it's not advanced, very, very new. So, and people are exploring different materials. So, honest answer is with the 2D, I'm not aware of the neuromorphic computing. But if I have to go with the 2D materials, which has the interface with the same, so I would go with the molybdenum sulfide.
Thank you, sir. I think you answered all the questions, and thank you, sir, for a truly enlightening session. Your explanation of how nanomaterials are reshaping the future of semiconductor devices was really fascinating.
We are
Thank you.
grateful for your participation and for sharing valuable research with our participants. So, before we conclude today's session, we request all the participants to kindly fill out the feedback form for technical session 8, the link for which has been shared in the chat box.
We thank our esteemed speakers, Ms. Nikita Gulia and Dr. Vinay Budraja, and all participants for making day 4 a success. Tomorrow, we will delve into the complete spec to SOC journey and the integration of AI ML in chip design. We look forward to seeing you then. Thank you and have a pleasant evening.
Yeah. Thank you. Have a good night. Thanks.
Thank you,
Thank you,
Dr.
sir.
Vinay. Thank you so much on behalf of the entire Department of Multidisciplinary Engineering.
Yeah. Thank you. Thanks. Thanks a lot.